Hello, Math 200 statistics students. We're on 2.5. 2.3 was measures of central tendency. 2.4 was measures of variability, aka spread. 2.5 is measures of position. In other words, where, if I am a particular data point, where am I in the data set? All right, so first thing we're looking at here are quartiles. In general, we're talking about fractiles. Fractiles are numbers that partition or divide an ordered data set into equal parts. Each part has the same number of data entries. For instance, the mean is a fractile because it divides an ordered data set into two equal parts. Sorry, the median, I think I said mean. The median is a fractile because it divides an ordered data set into two equal parts. So any number that can divide the data set into equal parts, whether it's halves or quarters or tenths or hundredths, is a fractile. Now, quartile is a particular kind of fractile. A quartile divides the data set into four parts, 4 quarters. Like 4 quarters make $1, right? So to do that, you need 3 different numbers, so that the first quarter will be below the Q1. The second quarter will be between Q1 and Q2. The third quarter will be between Q2 and Q3. The fourth quarter will be after Q3. So those 3 things, the Q1, Q2, Q3 quartiles, divide an ordered data set into 4 equal parts. About 1/4 of the data fall, well, I just described that, so I'm not going to say it again. All right, we're going to find the quartiles of this data set. All right, here's the data set. The first thing we got to do is put it in order. So I think the lowest one that I see is 6. The next lowest I think is 7. The next lowest is 8, and then 9, and then 10. All right, so I've gotten that one, that one, that one, that one, that one. 6, 7, 8, 9, 10. What's next? I believe 15 is next. Then 16. Then another 16. Then I think 20. And another 20. Then what? 23, 33. 23, 33. Then 50, 58, 104. 50, 58, 104. And that covers all of them. So that's all the data listed in order, least to greatest. Okay, to find the quartiles, the first thing I need to find is the median. So I'm going to start counting. I'm putting my finger on the 6 and another finger on the 104. And then I'm working my way in. I'm on 7 and 58 with my fingers. I'm working my way toward the middle. 8 and 50. 9 and 33. 10 and 23. 15 and 20. 16 and 20. And then the middle number is 16. This is the median. The median has another name. It is Q2, quartile 2. All right, so now this is the lower half of the data. This is the upper half of the data. So now I'm only looking at the lower half, and I'm going to find the median of the lower half. So I'm putting my left finger on 6 and my right finger on 16, and I'm going to work my way in. Now my fingers are on 7, 15, 8, and 10, and now they center in on 9. So 9 is the median of the lower half of the data. So this is called Q1, also known as the lower quartile. I'm going to do the same thing with the upper half now. My fingers are on 20 and 104. Now they're working their way in. I'm on 20 and 58, 23 and 50. And now they have both centered on 33. So 33 is the median of the upper half of the data. So this is called Q3, also known as the upper quartile. Okay, so the median or the middle quartile is Q2. So we have three quartiles, Q1, Q2, and Q3. So Q1 is 9. Gosh, that is ugly. Let me try that again. Q1 is 9. Q2 is 16. Q3 is 33. Now the Q2 is also known as the median. All right. We can find these same things whenever we do the one variable stats in our calculator. It also, so if we put all these data into L1 and then do the one variable stats as I have shown you how to do in previous videos, it shows you lots of great things that, the mean, the standard deviation, but some other things that it shows you is it gives you this information here. It gives you that information. It gives you Q1, it gives you the median, it gives you Q3, it also gives you the minimum, it also gives you the max. So if we were to say the min here, it would be 6, and the max here would be 104. All right, so those are the quartiles. Now let's go back to the book. Notice the book says the same thing that we just found. I also want just to remind you that what if you have two numbers in the middle? Like there's an even number of numbers, so you end up with two numbers in the middle. If you end up with two numbers in the middle, you would do let's say the 9 and the 10 were both the middle numbers. Then you would do the average of them so that your median there would be 9.5. But if there's an odd number of numbers, then you're going to have an odd, a middle number there. Okay. So back to the book. All right. We can use the technology to find quartiles. That's what that's about. We know how to do that already. I've already shown you how to do that in earlier videos. All right, let's read this example. About 1/4 of these colleges charge tuition. Oh, that's the answer. That's not a new example. Okay, moving on. Okay, new definition, interquartile range, IQR. The interquartile range of a data set is a measure of variation, so it's kind of like the previous chapter, the previous section, 2.4, but they couldn't show you this until you found the quartiles. Is a measure of variation that gives the range of the middle portion, so about the middle half of the data. The IQR is the difference between the first and third quartiles. So if we go back to our example that we were just looking at, the IQR here would be Q3 minus Q1, so it would be 33 minus 9, so the interquartile range here would be 24. That is the IQR for that example we did earlier. Okay, now that we know how to find the interquartile range, that's going to allow us to do one more thing with that, and that it gives us a more mathematical way to qualify outliers. Here is a way to do that. The guidelines, let's read them. We find Q1 and Q3. We find the interquartile range by taking the difference of those two things. We multiply the IQR by 1.5. So you do 1.5 times the IQR. Okay? Then you subtract 1.5. You subtract that number you just found in step 3, 1.5 times IQR. Subtract it from Q1. If there is any data entry that is less than that, it's an outlier. You will do the same thing, adding that same number that you found in step 3 to Q3. Any data entry greater than that is an outlier. All right, let us try to figure out if there's any outliers in this example, example 3. Okay, so we're going to do that to see if there are any outliers in this data set that we looked at earlier. So we've already found Q1 and Q3 and the IQR. So now we need to multiply the IQR by 1.5. So I'm going to say 24 times 3 over 2, which is the same thing as 1.5. That's going to give me 12, and that's so 12 times 3, that's 36. So 36. So 1.5 times 24 gives me 36. Now, what I do is I take Q1 and I subtract 36. So I'm going to subtract 36. 9 minus 36 gives me negative, that's going to be 27, negative 27. So negative 27, I look at that and I say, are there any numbers in my data set that is less than negative 27? No. No outliers to the left. Okay. Now I do the same thing to the right. I take the 33 and I say 33 plus 36. Okay, so I'm going this way. 33 plus the 36. That gives me, what is that, 69. Okay, so I look at that and I say, are there any numbers that are more or to the right of 69? Are there? Yes, there are. 104. So are there any outliers in this data set? Yes. 104 is an outlier by the mathematical definition that we have now applied. 104 is an outlier. Okay. Going back to the book. All right. Another important application of quartiles is to represent data sets using what's called a box and whisker plot, also known as a box plot. I always call it a box and whisker plot. It's an exploratory data analysis tool that highlights the important features of a data set. To graph a box and whisker plot, you must know the values shown at the top of the next page. Next page. So this kind of goes back to everything we've been doing in chapter 2, which is like how to display the data in a meaningful way. So these are what we need 5 things to be able to do a box and whisker plot. We need to know the minimum, Q1, Q2, Q3, and the maximum. Okay, this is what a box and whisker plot looks like. This would be called the left whisker, and that's the minimum. Over here, we have the right whisker. That's the maximum. And here we have a box. The left edge of the box is Q1. The right edge of the box is Q3. And then there's a line that is somewhere inside the box, not necessarily in the middle. And that is the median, aka Q2. All right, we're going to make us a box and whisker plot. All right. So we take the data that we did before, and let's see if we have any room. Let's go over here. So the minimum of that data set was 6. Q1 was 9. Q2 was, I can't remember, Q3 was 33. I think Q2 was 16, wasn't it? Yeah. And the max was 104. So I'm going to make a number line, and maybe I should count by 5s. 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 80, 85, 90, 95, 100, 105. 10, 20, 30, 50, 60, 70, 80, 90, 100. So my first whisker is going to be at 6. So I know they put a dot, but usually I put a whisker. But if you put a dot, that's fine too. I put a line for the whisker. They usually put a dot. All right. Then the left edge of my box is going to be at 9. So that's right here. Okay. And then the right edge of my box is going to be at 33. So that's going to be like right in here. Okay. Make my box. Pardon my really terrible drawing. It's the best I can do on this computer screen. That's the right edge of my box. So this is 6. This is 9. This is 33. And then I put a line in somewhere inside the box at Q2, which is the median at 16. That's going to be right in here. 16. And then my maximum is all the way out at 104. So here's 105. So 104 would be like right here. And I make my line go all the way to there. 104. So that's my box and whisker plot. And that tells me, that one graphic tells me a lot about the data set. And that's called a what? A box and whisker plot. All right. There are other fractiles besides the quartile. So here are some other fractiles. Quartiles we just talked about. Q1, Q2, Q3. Deciles divide the data into 10 equal parts. Quartiles 4 equal parts. Deciles 10 equal parts. So you call those D1, D2, D3, D4, D5 all the way to D9. And they divide the data into 10 equal sections. Then there's something called percentiles. Percentiles divide a data set into 100 equal parts. That's what, the word cent, that means 100, like century, 100 years, or cent, 1 cent. There's 100 cents in a dollar. So percent means per 100. So percentiles divide the data up into 100 equal parts. So you got P1, P2, P3, P4, P5, all the way to P99. And that divides the data up into 100 equal sections. Percentiles are often used in education and health-related fields to indicate how one individual compares with others in a group. Percentiles can also be used to identify unusually high or unusually low values. For instance, children's growth measurements are often expressed in percentiles. Measurements in the 95th percentile and above are unusually high, while those in the 5th percentile and below are unusually low. All right, interpreting percentiles. The ogive at the right represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. What score represents the 62nd percentile? So you can see it's kind of already drawn for you. All right, here is the percentile on the y-axis. Here is the score on the x-axis. So we look at the 62nd percentile. So you see that right in there, and you go over, you scroll over to this curve, and you find that data point right there, and then you go down and you see what score that is. So let's see, 50, 100, 60, 100, 70, 180. So it looks like 1600 represents the 62nd percentile. What that means, it means that 62% of the scores were below that score. If it's the 99th percentile, it means 99% of scores are below that score. If it's the 10th percentile, it means only 10% of the scores are below that score, which means 90% of the scores are above that score. Or maybe 89% of the scores are above that score. All right? Yeah, so the rest of that example just tells you what I just told you. In example 5, you used an ogive to approximate a data entry that corresponds to a percentile. You can also use an ogive to approximate a percentile that corresponds to a data entry. So another way to find a percentile is to use a formula. This is a useful formula. The percentile that corresponds to a specific data entry X, we use this formula. So if you have a specific score or weight or whatever, and you want to find the percentile of that data point X, then you do this formula. You take the number of data entries that are less than that data entry X, and you divide it by the total number of data entries. You multiply that result by 100. then round to the nearest whole number. Not up like we did before, but just to the nearest whole number. Okay, maybe we'll get a good example of it on the next page. All right, example 6, finding a percentile. For the data set in example 2, find the percentile that corresponds to 30,000. All right, so here is these tuitions. It says, recall the tuition costs are in thousands of dollars, so 30,000 is the data entry. 30. Begin by ordering the data. All right, so they ordered the data already for us here. And so here's 30. Now what do I do for the formula? I count the number of data entries that are less than this one. So since it's already in order, that'll be easy. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 goes on top of that fraction. Divided by the total number of data entries. Let's see the total. Total is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 12 times 2 is 24 plus 1 extra 1 is 25. So 9 divided by 25. Then multiply that by 100 and you get around 36. So $30,000 corresponds to the 36th percentile in these tuition costs for that data set. All right, the standard score. When you know the mean and standard deviation of a data set, you can measure the position of an entry in the data set with what's called a z-score. A standard score, which I always call a z-score. There's a formula for the z-score, and it is this. You take the value of that particular data point, you subtract the mean from it, then you divide it by the standard deviation. So in short, it's x minus mu divided by sigma. Or we could say x minus x bar divided by s, if it's a sample. And that gives me the z-score for that particular data point. All right. And what it tells me is, that number tells me the number of standard deviations that particular data point is from the mean. So if I have a z-score of 2.5, that means I am 2.5 standard deviations above the mean. If I have a z-score of -1, that means I am 1 z-score below the mean. Or I'm sorry, I said that wrong. That means that I am 1 standard deviation below the mean. Okay. Hope I said all that where you could understand it. I hope I said it clear enough. A z-score can be negative, positive, or 0. What does a z-score of 0 mean? It means that you are 0 standard deviations from the mean. It means that that data point is equal to the mean. All right. So let's see here. A z-score can be used to identify an unusual value of a data set that is approximately bell-shaped. So if you have a z-score that is 2 or more, or -2 or less, that's an unusual value because it means it's more than 2 standard deviations from the mean. If you have a z-score of 3 or more, or -3 or less, it means it's very unusual because it's more than 3 standard deviations away from the mean. All right. Moving on to the next page. Finding z-scores. The mean speed of vehicles along a stretch of highway is 56 miles per hour. So the mean is 56. All right. Mu. Oh, I can't write on that. I wish I could write on that. Anyway, mu is 56 with a standard deviation of 4. So sigma is 4. You measure the speeds of 3 cars traveling on the stretch of highway as 62, 47, and 56. Find the z-score for each of those speeds. All right, so 62, for the 62 mile an hour car, we say 62 minus the mean, which is 56, divided by the standard deviation, which is 4. And we get that car has a z-score of 1.5. It means that that car's speed was 1.5 standard deviations above the mean speed on that highway. All right, the next one, 47. You say 47 minus the mean, which is 56, over the standard deviation, which is 4, and you get -2.25. It means that that car's speed was 2.25 standard deviations below the mean speed on that highway. I think I'd be suspicious of that car for going so slow because it's very unusual. All right, and then the last one is going 56, so that's going to have a z-score of 0 because, you know, it's going the mean. So 56 minus 56 is 0. So you get 0 for that one. All right, example 8, comparing z-scores from different data sets. All right, z-scores can allow you to compare data from differing data sets. So, for example, if you're in one statistics class and your friend is in another statistics class, and let's say you came out with a 92 on your first statistics test, and your friend came out with a 93. And so your friend wants to say, well, look, it's obvious that I'm smarter than you, or I'm better at statistics than you, or if she just says that was better on this first test than you. You can say, no, they're two completely different classes, two completely different tests, so they're different data sets. What we need to do, friend, is compare our z-scores. And if you were any good at statistics, you would have known that. So you let me do we can do the example that they give. The table shows the mean heights and standard deviations for a population of men and women. Compare the z-scores of a 6-foot tall man and a 6-foot tall woman. So if you have a 6-foot tall man, all right, they're doing this in inches, by the way, not feet. 6 feet is 72 inches. Look, the mean height for men in this data set is 69.9. The standard deviation is 3. The mean height for women in this other data set is 64.3. And the standard deviation is 2.6. So get the z-score for this 6-foot tall man. You say 72 minus the mean of that set, which is 69.9, divided by 3. His z-score is 0.7, which means he is 0.7 standard deviations above the mean for the height for a man. Now do the same thing for the woman, and hers would be 72 minus the mean for that data set, which is 64.3, divided by the standard deviation for that data set, which is 2.6. And you get that her z-score is 3, which means that her height is 3 standard deviations above the mean height for a woman. All right. So that the woman who's 6 foot tall would be unusual. The man who's 6 foot tall would not be too unusual. All right. And so that is it for section 2.5. We're done with chapter 2. Yay. All right. Good luck on section 2.5. We will stop and have a test over chapters 1 and 2. And I'll see you again on videos for chapter 3.